Hi, everybody. Thank you for coming. How's everybody doing here? Great. Cool. Did you guys catch the keynote? Yeah. That was awesome. So my name is Anuj Gosalia, and I'm going to talk about building with the Oculus Rift using the PC SDK. So in this talk, I will go over some of the internals and architecture of the SDK and show how to use that information to build great VR apps. I will also introduce the Oculus Touch APIs, and then I will talk about approaches to get great performance and lowest latency for VR. And finally, I will end with some thoughts on where we're headed and ideas for upcoming work. So as you all know, VR is very demanding. Trying to drive high resolution at low latency in glitch-free fashion just pushes the limits of systems in ways very few problem spaces do. For the Oculus Rift, our panel resolution is going to be 1080 by 1200 pixels per eye. However, we want to render our eye buffers at even higher resolution. We would recommend 1350 by 1600 pixels per eye for our eye resolution. And that's to account for the lens distortion that we have. But because of the wide field of view, the pixels per arc second that you would have is still a lot lower than that high resolution would indicate. And so we still really need to spend a lot of time and effort on each of these pixels, and we need good anti-aliasing techniques in addition to the high resolution that we're drawing at. So we're looking at approximately rendering about 4.3 megapixels for a stereo eye pair per frame. And since we are rendering in stereo, it requires most of the scene to be drawn twice. So there's just a lot of rendering work that needs to happen for VR. And if that's not hard enough, we also really need really low motion to photon latency. And to get that, we're driving our panel at 90 Hertz. And mostly making 90 Hertz is not sufficient. We want to hit 90 Hertz at really high probabilities. Ideally, we want to get 5 nines of reliability in hitting that frame rate, since every glitch can reduce comfort. So to reach these kinds of render rates at high resolution, we're looking to push about 400 million pixels per second. So that's going to require a really powerful machine. And with this in mind, we came up with a set of recommended specifications that is a pretty high-end machine spec. And this ensures that users have a great PC when they attempt to run VR. It also enables the developers to have a great baseline to target and know what to optimize for. And that allows them to have a high chance of getting really great performance for VR. We have picked very high-end GPUs, which happen to be the most important component for VR. That, along with the really relatively powerful system that we're talking about, this allows you to get roughly 8K flops of math operations per eye buffer pixel, and you get about 120 I/O operations, which means you can do about 120 pixel reads or pixel writes per frame per pixel before you saturate the memory bandwidth of these GPUs. We are talking mostly about desktops here, but some very recent upcoming high-end laptops and notebooks are finally supporting this kind of a spec, and we expect to see more over time. I also highly recommend, if you're developing an app, to try and get a system with NVIDIA and an AMD GPU so that you can make sure that your app runs well on both those configurations. Let me recap some of the recent work we've done so far. Over the last few months, we've shipped a few major SDK releases. Just after GDC, we shipped SDK 0.5, which is mostly a move to the DLL model, where we took a bunch of our code and took it outside the app's executable. Then, in 0.6, we shipped two key things. One of the biggest changes there was a move to the VR compositor architecture, which is part of our trend to build a robust and stable architecture, and I'll talk more about that later. We also introduced the feature of layers that can help with performance and quality. The next release, 0601, we added some amount of Q-head to get better efficiency, and we also introduced the performance heads-up display to help developers understand and debug their performance in real time. And finally, our last release was 0.7, which we did last month, where we introduced something that we call the direct driver mode, which is an evolution of what we have been doing in past with direct mode. We've also removed extended mode because it was fragile and we want to focus on one robust way of doing VR. We've also added in 0.7 the input APIs that supports Oculus touch controllers. And finally, we've added Windows 10 support. Along the way, we've been providing integrations for the two most popular game engines, Unity and Unreal. Here are the various engine versions and the Oculus PC SDK versions that they support. Apps developed for any of these engines will work with the latest 0.7 runtime. Note that in addition to these out-of-box integrations that come with Unity and Unreal, we provide up-to-date Unreal integration source on GitHub. So you can look there to get the latest SDK support. Now, let's take a deep dive in the internals of our software. I'll do an overview of our architecture. So one of the big changes we've done over the last few months that really helped us get to a more robust architecture is this notion of the VR compositor. The key idea was to isolate VR processing from the app. In past, we used to share and use the same process and same thread that the app did and use the app's rendering device and swap chain and use the app's HWind to do VR. At the same time, the app was using all of these resources to do its own iBuffer rendering. And that led occasionally for these components to step on each other's toes. The solution was to move the time warp and distortion work into a separate process and a separate thread that has its own render device and swap chain, and that is no longer using the app's HWind. This allows our compositor to take care of the tricky handling needed to get really low latency VR, and it gave the app freedom and flexibility to render its iBuffers using its own graphics resources. By giving the control of its HWind and swap chain back to the app is free to render whatever it wants to its window, which could be the mirror view of what's happening in VR or any additional information that it may want to show. From an architecture perspective, what you see here is that we've removed a lot of code out from the app's process and moved that into the VR compositor process. For instance, in the past, the direct mode driver, these two components, would run inside the app's process. And now with the VR compositor, a lot of the compositor work and all of our driver work is no longer in the app's process. And this makes it less likely to impact and affect the app's code. And with our latest direct mode driver, we have, for all practical purposes, removed the need for our direct mode driver, which was sitting in between the IHV driver and the Windows graphics stack. And we've moved this functionality into the IHV drivers. We have one less component, and with it we've eliminated the set of stability issues that came from its presence. And this, we believe, will be the most stable way of powering the Rift and ensuring that we have a direct and low latency connection to the Rift that is hidden from the OS. This work was done in cooperation with NVIDIA and AMD, who have been great partners to help us achieve this. This diagram helps you understand how the VR compositor works from a timing perspective. So what you see here is an app that's making frame rate. It does some work on the CPU to submit rendering calls, which then get executed on the GPU at some point later. And once the app finishes submitting all its rendering call, it calls a submit frame API, which then informs our compositor to do the time warp and distortion work in its own process. And this time warp and distortion work eventually gets queued to the GPU to execute after all the iBuffer rendering is done. And so in this model, you have a typical app that has 1 frame of render latency, but because of time warp, our time warp latency is a lot smaller. So there are some interesting implications of this architecture. In the past, we used to have this call configure rendering, where the app would pass us the graphics resources that it was using. We no longer need that. Instead, what we need is the app to call into the compositor to allocate a set of shared iBuffers. These will be something that the app will render to, and then the compositor will compose from and distort and present to the screen. So the create swap texture set APIs allow the app to create what is the logical equivalent of a swap chain, but for VR. And then when the app is done rendering to these shared iBuffers, it submits them to the compositor by calling OVR submit frame. And this is the model equivalent of present or swap buffers. One of the things we want the app developers to do is try and not render to their own swap chain and then copy the results into these shared iBuffers. We want you to set these iBuffers as the render target and draw directly to it so that you don't have an extra copy every frame. So now let's look at some tips and techniques to use our SDK to build great apps. There are many forms of multi-GPU configurations, and some are getting increasingly common. At the high end, there are SLI and crossfire configurations. By default, they don't help much and even hurt in some cases. But with NVIDIA GameWorks VR and AMD's Liquid VR extensions, a VR app can use them to a performance advantage. So that, if you're willing to target SLI and crossfire, you can use these extensions, and then you can actually make it work well on SLI configurations. Hybrid GPU configurations are where you're mixing integrated graphics and discrete graphics, and these can be problematic. In particular, hybrid laptops are not supported because they often tend to have the HDMI output connected to the integrated GPU, which is too slow. These days, even most desktops with discrete GPUs have the integrated GPU enabled. This can be made to work along with other multi-GPU configurations, but on these machines, we need the compositor and the app to agree on which GPU we should use. To get this right, OVR create API, when you create the HMD, tells you which GPU the headset is connected to. And that is the GPU that the compositor will be using, and that is the GPU that the app has to use for this to work. So ideally, we want the app to create all of its graphics resources after it calls OVR create. However, we know that many apps do their graphics resource initialization pretty early in the process and well before they've enabled VR. If you do this, then still make sure that you check the return value of the adapter from OVR create, and if that doesn't match the GPU that you created all the graphics resources on, then you want to restart and recreate everything. So another thing that we've changed because of that is that the lifetime of the HMD object is now limited to the time that the headset is actually connected. This is because, in theory, if the headset gets disconnected, there's no guarantee that it'll come back to the same GPU. So OVR submit frame now returns an error display lost in 2 conditions: if the headset got disconnected, or if Windows detected a graphics timeout and recovered from that. Typically, this happens when the headset is disconnected and the app and the user will most likely reconnect it back to the same GPU. So in this case, you really just need to recreate your OVR HMD object. You need to recreate your texture swap sets because those were shared with the GPU that the headset was connected on. And if you're using a distorted mirror functionality, then you need to recreate your distorted mirror texture. You do not need to recreate your graphics resources in general. They will survive, and you could switch to 2D rendering if the headset is disconnected, or wait till the headset gets reconnected. However, in the case that the headset got reconnected to a different GPU, then you need to recheck the GPU ID returned by OVR create again and see if you need to recreate your graphics resources. So make sure your app is aware and robust in face of things like Windows, graphics timeouts, and headset connect disconnect. Another thing we introduced is this notion of VR app visibility. If your app does not have focus, it will not be visible. This can happen in multiple cases. For example, we could be showing the health and safety warning, or we could be in our home app, or some other app could be running. In these cases, OVR submit frame will return not visible success code. At this point, the app should pause rendering and simulation and animation and anything else it's doing, and just poll OVR submit frame till the return code changes. The key point is not to consume a lot of CPU and GPU resources in this mode, so that any other app trying to do VR has all the resources available to it. Another thing that's important to get right is timing and prediction. So let's talk about the simple case of a single-threaded app with its simple render loop. What we want to do here is that we want to first predict when the next frame is going to be drawn. And so you get that by calling getFrameTiming API call. And then you get the display midpoint in seconds value that tells you when we expect the next frame to be drawn. Using this, you then try and get a predicted pose at that time. So you call getTrackingState to get the predicted pose and pass the time that you want the predicted pose at. Once you get the predicted pose, then you calculate the I-poses from it and then render with these I-poses. So from a timing perspective, here the app at the start of rendering, it samples the pose, but it's sampling the pose out into the future at the next frame. Actually, it's sampling it at the midpoint of the next frame, but just for simplicity, I drew it at the vsync that designates the start of the next frame. And so each frame, we are sampling the pose out into the future. We typically want to sample the pose as late as possible. So if the app has work that it can do that is view independent, you want to do that first and then predict the pose so that you have the most up-to-date and you're predicting out as less as possible. So if you have game simulation and physics that you can do ahead of time, then that would be helpful. Also, if you can do parts of your rendering with an approximate view and then refine the view just before drawing the left and right eye buffer, then that would be also a recommended approach. Though, make sure that you're using the exact same pose for drawing both eyes. Do not sample the pose again between left and right eyes. So here's an example of the app doing some pre-work where it's sampling the pose, and that's approximate pose, but then just before drawing the left and right eye, it's resampling the pose, both of which are predicted out in the future, and it's getting a better refined version of the pose just before drawing its eye buffers. Many game engines and apps can be multi-threaded, and so it can have a game or a simulation thread that is running ahead of the render thread, which would be the one making the graphics API calls and VR API calls. And each of these threads possibly may need an I-pose too. Now, the longer out you predict, the less accurate the pose is, so we would ideally want to keep refining the prediction over time. So here's what that could look like. Here you have an app which has a simulation thread that is, say, simulating frame 2, while the render thread is rendering frame 1. And then eventually the results of that simulation are picked up by the render thread to render frame 2, which then eventually gets sent to the GPU that gets scanned out at this vsync and on out. So in this case, the simulation thread is going to sample the pose once, but it's sampling the pose 2 frames ahead. It's trying to figure out what the pose would be at this vsync. In addition, you have the render thread that is going to resample the pose and predict out a little bit further out, and of course our time warp distortion will also sample the orientation again just before it does the distortion. And so we are continuously refining our pose prediction as we go along in this pipeline, and each one is refining the period of time, how far out it's predicting to. And obviously the simulation thread will also continue to keep resampling the pose further out as it goes along. So as you can see here, we are actually doing a whole bunch of sampling of the pose with different prediction periods, and so it can get tricky to make sure that various threads that are sampling poses at various times out get this right. And it's really important to get the timing and prediction right, because otherwise you'll get subtle errors in the pose that can make it be less comfortable. So to help with this, we have introduced this concept of a frame index. What the frame index is it helps you correlate multiple calls from multiple threads to these things by saying that referring to each frame by a frame index. So you come up with a monotonically increasing value to refer to each frame, and the actual value is not important, but you can start with any non-zero value, say like 1. And then if you use a frame index, you use it consistently to say, hey, get me frame timing for frame 1. Then you can call again and say, get me frame timing for frame 2. And you can mix calls across threads for frame timing on arbitrary frames. And since you're now referring to frames with a frame index number, the API knows which frame you're referring to. We also need to make sure that if you're using frame index, you also use the correct frame index on submit frame, because that allows us to know which frame exactly is corresponding to the frame index. So that's how we establish the correlation between the frame index and the actual frame that got scanned out. You can use 0 if you don't want to do this correlation. 0 is just a shortcut for give me the next frame. And so that works well for simple single-threaded apps. And so some of our samples do that. So here's what that could look like. In this case, you could say that, hey, sample me pose for frame 2. And then this one says, sample me again the pose for frame 2. And this guy would do that again. Meanwhile, the simulation thread at the same time is saying, sample me pose for frame 3, and so on. And so you can basically have intermix calls of sampling pose of get predicted time and get tracking state. And if you use the frame index, it allows us to refer to the right frame for the right call. Another thing that we changed is the way we handle sRGB color space. In our older SDKs, we assumed that all iBuffers contents were in sRGB. However, it caused problems if the surface is actually marked as sRGB, because we just assume that by default everything is sRGB. 0.7 actually pays attention to the sRGB formats. So if you use DXGI or OpenGL to tag a texture as sRGB, we will treat its content as that, and then anything that is not tagged as such will be treated as being in linear space. This allows us to use the GPU to properly convert from linear to sRGB or sRGB back to linear as appropriate every time it's either sampling from these textures into the shader or writing values out from the shader back to the render target. That is the most recommended way of doing color space conversions. If you have an app that has some need to do custom color space conversion, then we have this option to create our texture swap sets as typeless. What this lets us do is that we can make sure that that texture appears as sRGB to our compositor, so it knows that the values of the resource are in sRGB space. But if the app wants to render to it using custom linear to sRGB conversion in the shader, then it can map that resource as linear as an output to the as a linear render target, and then do custom conversions in the shader. I'm not sure if that's the most recommended thing. I think we found it just best to let the GPU do the conversions on writes, but it's an option. Next, I wanted to talk about our touch APIs. So our touch APIs support controller tracking. It gives you the values of the button states. It also gives you values of the touch state of each button. And then we have analog triggers and thumbsticks that will give you analog values of their positions. And finally, we have what we call finger poses. This is a high-level state of how your fingers are positioned based on touch state. So it's something that we infer. And then finally, we have ability to set vibration on these controllers. To get the tracking state of the controller of where it's positioned in space and how it's oriented, we use the same get tracking state function that we use for our headset. We've added a hand poses member variable to this tracking state structure that gives you the left and right hands position, just like it would give you the headset position. We use the same constellation system to track the controllers, and this system allows us to use the same feature set that we have for the headset, like it supports things like prediction and so on. In addition to track state, we also have a structure called input state that allows you to get all the non-track state. There's an explicit API called get input state that returns the latest values for the non-track state in this structure. So we have a field time in seconds, which allows you to know when was the last time that the latest change of button state happened. So you can correlate this with the timing that is done for the tracked state, so you know exactly which place the controller was when that input state or button state changed. You can there is a connected controller type field, which basically gives you connectivity status. It tells you whether the left controller is connected or the right controller is connected or both of them are connected. Then we have a bit field called buttons, which gives you a boolean per button, whether it's pressed or not pressed. We have another bit field called touches, which is the same set of enums of on a per button basis. It tells you if the finger is touching that button or not. Touching a button is just a matter of it's a touch state. It doesn't mean that it's been pressed. And so the button state tells you whether it's pressed or not, and the touch state just tells you whether somebody is touching the button or not. And then we have index and hand triggers. These are analog triggers, and so you get a value between 0 and 1 to tell you the status of those triggers, and you have 1 for each hand. And then finally, we have a thumbstick, which gives you a two-dimensional vector giving you values between -1 and 1 for each x and y direction, with 0, 0 being that the thumbstick is at rest pose. We have this concept of finger poses. This is actually a higher level state that is inferred from the button touch state, and so it has some hysteresis and latency to trying to figure out reliably whether the finger is pointing up or the thumb is pointing up, but it's still returned as a bit field inside the touches bit field. So we have ways to figure out if the index finger is pointing out or not, or the thumb is up or not. And this can help a lot with some common gestures and gives you a really important part of hand presence. And finally, we have an API to set the vibration of the controller. You can set the amplitude, and by setting that to 0, turns off vibration. And right now we have a couple of frequencies that you can set to vibrate it at. This is an area that we're looking to add more functionality moving forward, but it's a basic start of what we support today. So now I'm going to talk about how to get good performance and latency out of VR. So this was the compositor timing diagram I just showed earlier. One thing to notice here is that while we sample the time warp pose at this stage, it's not actually consumed by the GPU till this point. And so the observation is that there's a time delta from when the CPU queues the work to when the GPU consumes it. And we could have new pose data available in between that. And so we use this concept of late latching to try and pick up at the GPU level the most up-to-date state of the pose that could be available. And we do this by just having a volatile constant buffer that the CPU keeps updating, and then the GPU latches that latest pose just before it renders. And so when we do late latching of orientation, you can see that instead of just sampling the pose here, we pick up a more up-to-date value of the latest sensor fusion value that we may be getting just before the GPU is ready to do the time warp and distortion. And so this reduces the time warp latency, even though of course the render latency stays the same. Another thing to talk about is GPU efficiency. In traditional 3D graphics, the most important thing we focus on is to parallelize CPU and GPU work. Our goal is to avoid bubbles of idle time in GPU utilization. However, for VR, we are biasing for latency over efficiency. And so you have situations where you could have a glitch even if the CPU or GPU are not saturated. So here's an example of that. In this case, the app has some amount of CPU and decent amount of GPU work, and since it didn't get sufficient parallelism between that, it glitched here. However, if you notice, the GPU is not fully saturated, and neither is the CPU, but we still ended up glitching here. One way to avoid that is to do something that is called queue-head, where you basically try and parallelize some amount of the CPU work with the GPU work. This basically means that we will start rendering a little bit ahead of vsync and allow some amount of parallelism. By doing this, we've taken the same scenario and now the frame can make it just before vsync, so we don't glitch. However, we have increased the render latency a little bit more by doing the amount of queue-head. So instead of starting here, now we are starting to sample the pose at this point for rendering, and so we have increased the render pose latency somewhat. And for apps that did not need queue-head, we also increase the time warp latency by moving everything to the left and doing a queue-head. And so this is basically a trade-off between latency and efficiency. What we have found is doing about a quarter frame of queue-head seems to be a sweet spot. It gives us a huge amount of the parallelism that we would like, and it still doesn't take away from comfort as much. And so we've set that as a current default in our SDK. However, it can be disabled if your app does not need that extra headroom. Another feature we've added recently is the performance heads-up display. This lets you see performance and latency stats and other useful information live on top of an arbitrary VR app. It can be enabled programmatically or via a configuration tool. So I'm going to explain some of the stats and metrics, some interesting metrics that we have there. The first one is what we call the app tracking to mid-photon latency. What this is showing is that it's measuring from the time the app has sampled the pose, which may be not the first thing, but when it finally does sample the pose, from that point all the way to when that frame actually scanned out, and we take the midpoint of the frame when that is scanned out, and we measure that using a latency tester to know when that frame actually was displayed onto the headset, and we use a midpoint as a metric, and we measure that time from when the app sampled the pose to when the midpoint of when that frame actually got scanned out. And so that's the app tracking to mid-photon metric. Similarly, the time warp to mid-photon metric that you'll see in the Perf HUD measures the time from when we sample the pose for the time warp to the mid-photon point when it gets scanned out. The next metric is app render GPU time. This measures the complete time from the first work that the app sends to the GPU to the last point. And to show there can be bubbles in the GPU utilization when you do this. And so this metric is not an exact use of how much GPU time it took to draw your frame, but it's more of elapsed time from the first point to the last point. And this is important to keep in mind because as you tweak your app and change things, you may see this value change in non-intuitive ways, like it may jump more, and that's just because you just stepped over a bubble or not. So just watch out when you look at this value change. The next metric we show is the app render CPU time, which is basically the complete time that the app took between subsequent calls of submit frame. And so this is the entire time that the app took. This is where the app was returned from submit frame, and then when it finishes rendering the next frame, this is when it calls submit frame. So that's the app render CPU time. And finally, we have the compositor GPU time, which basically shows you how long it took us to do the time warp and distortion work that the compositor does. And this is typically proportionate to the iBuffer resolution. It's proportionate to the kind of layers and other features that you've turned on for the compositor. So as we talked about, we have very large iBuffers, and that's because we need to have our distortion mesh samples finely at the center and much more coarsely towards the edges. And so we really need large iBuffers to fully resolve the center pixels. But drawing these large iBuffers sometimes can be really hard and make frame rate. One common technique is you can drop resolution, and that can be pretty effective in most cases, though of course you can't see it on the screen, but it's not that obvious when you shrink down the resolution. It's more obvious in VR, of course, not on the screen on a projector. But even if you look closer, you can probably see a little bit of lost details in the ripples in the pond, but it seems a viable way to go, and it's better than missing frame rate. The problem with this is if you have high frequency detail, especially like text. Text readability can suffer a lot as you shrink down the iBuffer resolution. So we have this feature of layers that basically says that you can have multiple sets of iBuffers that you can compose. What this allows you to do is it allows you to pull out 2D UI into a separate pair of iBuffers. These 2D UI iBuffers can be relatively larger size because they're not expensive to render, and they can be sampled in high quality. Whereas the world scene can be in a separate iBuffer that can be relatively lower size, or it can be scaled down to make sure that you can hit glitch-free rendering, because that tends to be much more expensive. And then our time warp distortion will compose both of these buffers to create the final scene. And so by doing that, you can have UI panels like this where the text legibility is maintained. And here we show a drastic case where we shrink the iBuffers down to 10%, and of course the scene gets pretty blurry, but you can still read the text. Another observation is that these chords of layers, they don't need to be all exactly aligned with the iBuffer. We can have a chord be at arbitrary orientation, and we can sample from it. And so we basically have layers of chords in arbitrary world space, in arbitrary orientation in world space. And this allows interesting use cases. One another advantage of doing this is that it actually gets you slightly better quality, because without layers, an arbitrary chord in world space would get sampled twice. You'd first sample it once to draw it into the iBuffer, and then we'd resample it when we do the distortion. By having a chord in world space layer, our distortion code directly samples from the original chord texture, and so you get better filtering as a result. Finally, I wanted to talk a little bit about some ideas of what we're thinking about moving forward. So the first big thing that we are focusing on is what we call the SDK 1.0. As you heard this morning, we are trying to get to this starting December 2015. The aim of this is that this will be the API that will have long-term compatibility and support. So apps written to our SDK 1.0 can show up on our store at launch and will be supported for the foreseeable future. Note, this is not going to be our final API. We fully intend to continue working on adding new features and new functionalities and improving things in our SDK on a regular basis. However, after we hit SDK 1.0, all of those changes will be done in a non-breaking and in a compatible fashion. So we'll be mostly additive changes. We hope to get up-to-date Unity and Unreal integrations that support our SDK 1.0. We are currently hoping to have Unity 5.3, also Unity 4.6, and then Unreal 4.11 support our SDK 1.0. Between now and then, we will continue our pattern where pre-1.0 SDKs will keep supporting the current API of that SDK and one older API. Like we do for 0.7, we support the 0.7 API and the 0.6 API, and 0.6 supported 0.6 API and 0.5. So we will continue this approach till we hit 1.0, and then when we hit 1.0, that API will be long-term compatible. We're looking at a bunch of different things for future SDKs, and I'm going to talk about some of these ideas. None of this is a plan of record or guaranteed to happen, but just these are the things that we are looking into. One of the big things that we are really excited about are these modern graphics APIs like Vulkan and DirectX 12. We really think that these are a very good fit for VR. They are low level, they give a lot more control to the developers. They're designed for extremely high performance. Their changes and design for multi-threading is actually a really good fit. We've seen a lot of cases where apps struggle to make frame rate if they're loading some resources in the background. And some of these problems go away when you use these modern multi-threaded friendly APIs, graphics APIs. They were designed for these scenarios. So I think that this is going to be a really big win. And we're working with Unity and Epic to make sure that as they move their engines to these modern APIs, we work with them and have great support for them for VR. Another area we're looking at is some enhancements to the input APIs. We're pretty early stage of our touch APIs, and we've been thinking about how to improve it moving forward. One concept we think which will be very important for dealing with input controllers in VR is that the end user can't actually see the controllers in their hands because they have a headset covering their eyes. And so it's going to be an important concept to make sure that you can visualize the input device and have some sort of input guides. You may have seen that in some of our touch demos with hands and so on, but this is even important for games that are using the Xbox One controller. And so we're thinking about adding a concept of an active input device, because you have multiple input devices that the user could be using, so it's important to know which one the user is interacting with at any given moment. And by knowing that, the app could potentially show the appropriate input visualization. It won't be any good to show hands if the end user is actually using a controller, an Xbox One controller, for instance. And so we're thinking of adding a concept of an active input device. And we're also looking at potentially adding support for the Xbox controller to get the Xbox controller button states via the same get input state API function that currently returns you the touch controller state. And so you will have one unified input API that allows you to know which controller is active and then what is the state of the active controller. We also are thinking about taking this idea of late latching beyond just for our time warp, but also for apps to use it for its render pose. So the idea here again is similar. We typically sample the pose here, but then the GPU is just using the pose at this point. And so in theory, we could late latch a more up-to-date sample of the pose just before the GPU is about to draw the left and right eye. And by doing that, we again reduce the render pose latency compared to what it would have been if we didn't do the late latching. So to make this happen, the app would have to implement a persistent mapped constant buffer, which is something that D3D12 and OpenGL support. And we've been able to emulate that on D311 by just using map no override. And this seems to work well on all the modern graphics drivers. The app would need a separate thread to update the pose values, and we're considering potentially adding an API that informs the app when a new pose is available so that it's not just busy writing the same value all the time. And then the app would have to write some code at the start of rendering to copy these volatile constants into the camera constants, and it needs to do that just before rendering the view dependent parts. And this allows, you have to make sure that once you do that latch, you use the exact same value consistently throughout the rest of rendering, otherwise you'll get tearing artifacts. The other thing that you have to be careful of is the fact that you have these volatile constants that the CPU is writing to, and eventually the GPU is going to latch and copy from it. And so you can have a race condition there. And what we found is that by using a circular buffer, we can avoid that race condition. And the amount of circular buffer you need to actually solve it in practice is not too bad, because our sensor fusion thread is updating pose values once every millisecond. And when you consider modern GPUs or the recommended spec GPUs, they don't take very long to copy a handful of constants. And so we don't really have a large window of time that this happens. So just having 3 to 5 item long circular buffer is sufficient to ensure that there's no race condition between the CPU writes and GPU reads. And this avoids complicated CPU-GPU synchronization issues. Now, of course, the mechanics of this make sense, but there's some interesting, tricky things that happen if a complex modern game engine is actually trying to deal with this. A game could have CPU-dependent work that's happening, CPU work that is view-dependent that's happening, like culling or collision detection and so on. And so you could cull the scene with one view, but then render pose late latching is going to change that underneath you when it goes to the GPU, and so that could not look right. You could solve that by expanding the cull volume to be more conservative to account for that. Another thing that we found, a technique that we found actually very useful when we were experimenting with this, was to do just position late latching. The idea here is that instead of late latching the entire render pose, you just late latch the position aspect of it. And the thinking is that the orientation aspect is going to get fixed up by time warp anyway later on. And so this also has a couple of other advantages. One, it simplifies passing the iBuffer pose to submit frame. We no longer need to worry about what are the latest pose that got latched by the GPU and make sure we communicate that back to submit frame. Also, we found that it reduces culling mismatch, because you can actually move the orientation a lot very quickly, but positional changes are a lot more subtle. And so if you just late latch the position and let time warp take care of the orientation changes, when time warp fixes up orientation, you don't see culling artifacts, you just get a black pull-in, which is actually a lot less objectionable than seeing through aspects of your geometry that might have been culled. And so that seems like a promising approach that we're going to explore and potentially add APIs to enable apps to do. Another thing you've heard us talk a lot about in past is asynchronous time warp, or ATW. We've used this very effectively on the mobile product, and we've been actively working on this to see if we can bring this to the PC. So the basic concept here, in case you're not familiar with it, is that if an app is occasionally going to glitch and it has a frame that misses the vsync time frame, instead of having a glitch, you want to pick the old rendered iBuffers that were available and then re-time warp those old buffers and then preempt the rendering of those iBuffers to get a time warp version of these old iBuffers that can be drawn at the upcoming frame. And so this basically says that it's better to take a time warped version of the old frame and make frame rate than to glitch. This of course relies on preemption, and GPU preemption is not an exact thing like it is on CPUs. And so GPUs can take a bunch of time between when you ask it to preempt and when it actually can preempt rendering. And so we end up pulling in the time we have to actually do time warp for ATW to account for preemption granularity of the given GPU. And of course, the preemption granularity is not small in many cases. So some GPUs take a really long time to preempt. And so we need to expand that out and pull this quite a bit in the ahead to make sure that there's a good probability of making sure we can get at least a distorted version of the old frame in. A side effect of this kind of starting early to do ATW is that there will be some cases where an app or a frame that would have otherwise made it, we end up just preempting it and rendering with the older version instead. And so in these cases, we are basically increasing the render pose latency, even though the time warp latency stays mostly the same. So ATW is again a trade-off between jitter and positional latency. And as I mentioned, GPU preemption is still pretty uneven, though it's really getting better with each hardware generation. And also, there's some challenges to actually achieving this on Windows operating systems. And it turns out with new Windows 10, this has gotten a lot better. So we're a lot optimistic about our ability to try this. So we have a lot of interest in trying to see if we can make this work. And we think this has a good potential to smooth over glitches. But like anything, this is not a silver bullet. So we still need the apps to focus really hard to ensure that they're doing everything they can to make frame rate. Then there's a whole bunch of other stuff that we're looking at, and I'm by no means going to do an exhaustive list of that. We're looking at techniques to better utilize the GPU power on the parts of the pixels that matter most and not on the periphery where we are undersampling anyway. There's a range of techniques that one can do to basically have different levels of rendering on different parts of the eye buffers. One class of techniques is to just use multiple viewports per eye, and these are just ways of trading off increased vertex cost to save pixel cost. And some IHVs have extensions to help with multi-viewport rendering. And then we've been talking with IHVs for the long term of ways to be more adaptive at rendering rates, rasterization rates, or even shading rates, such that we can be more judicious of where we spend GPU resources, such that we can actually reduce the amount of time we spend on the peripheral edges of the eye buffers. Another big area of investment for us is developer tools. We're going to be spending a lot more time on this moving forward. We want to add a lot more performance instrumentation, more real-time visualization like we're doing with the Perf HUD. We want to give more programmatic access to these stats that the app can use for its own validation and so on. We want to have modes where we can collect all these stats in a trace that can be then analyzed offline. We want to add more stuff to our debug logging to make it more informative. So there's just a ton to do here, and this is something that we are going to keep investing over time. This is going to be a big help because getting performance and latency sensitive apps running well really requires great tools to make this happen. And then more future investigations. There's just a lot of, this is no way a full list by any means. It's just out there to throw out some ideas of things that we have been talking about and we'll continue to look at. So positional time warp is something that we've been experimenting with to see if that works. We can extend the notion of the kind of primitives we're using for our distortion phase. Right now it's a bunch of chords, but we could do other things like cube maps or something else. And then there's this general technique of decoupled rendering that might be viable with new APIs like DX12 and Vulkan, where you could have a render thread that is mostly rendering existing command buffers and doing some basic head tracking and small animation interpolation. And then you could have other game and engine threads that are doing much more expensive simulation and game rendering and creating all these command buffers. And they could, in theory, be not running in lockstep, and they could be running at different rates. And there's some interesting artifacts and interesting issues to think through to make this happen. but it seems like a promising approach to go and consider moving forward. And I'm looking forward to ideas from you guys to see what other techniques and things that you think we should be looking at as part of our future SDKs. So I'll be around and over the next few days, so if you have any cool ideas, I would love to hear that. So to wrap up, we are at an amazing time when we have almost ready to launch consumer VR on mobile, on PC, across multiple IHVs. So this is an amazing moment for app developers to build great VR apps and experiences. I recommend you all to focus and target the recommended spec. This allows us to make sure that if a user has the right machine, they get great VR experience. Try out our touch APIs. We will have a program for developer access to the touch controllers coming up soon, and we'd love to hear your feedback. This allows a huge amount of interesting things to be done with hand presence and the kind of interaction models it allows. I want to re-emphasize, when you are optimizing for VR, please focus on hitting frame rate over just adding more visual quality and oomph to it. And finally, I want to plug a talk that's coming up tomorrow from some of our engineers who will be talking about how to integrate user API and samples to integrate VR into an existing engine. And also they will talk a little bit more about perf analysis and how to use tools like GPU View to do that. So that's tomorrow at 11:30. I think that'll be a great follow-on talk for people to get more information. And with that, I want to open up for questions. There's a mic at the back, so if you walk up to that, everybody else will be able to hear your question. And I have a few minutes to, I'd love to see if you have any questions.
Right up there. I just wondered if there's ever going to be an option to disable the safety warning.
So the question was, will there be an option to disable the safety warning? We are definitely rethinking and looking into what is the right frequency and ways to show the health and safety warning. We want to find the right balance of making sure people understand the risks of using VR, but not be annoying where it's happening too frequently. So yes, we're absolutely looking into ways to do that. I don't think there will be a programmatic way for whatever policy we pick. We want to make it less intrusive, but it's not something that we think we can just have people blanket disable completely, because that would be dangerous.
So with the touch APIs for getting the touching and the button pressing, have you guys dealt with the fact that potentially the capacitive touch could not be triggered when the button is being triggered? Is that some state we need to account for, or does the input state itself already say, hey, if the button is pressed, touch definitely is pressed?
That's a good question. We expect those things should be consistent, and so if they're not, then that's a bug. And moving forward, we'll have more validation that ensures that that thing doesn't happen. But today, we have different electrical sensors that return button press, which is a physical contact, and a capacitive touch. And in theory, that should not happen, but there can be corner cases where that may happen.
That's something that we should be checking, or have you guys dealt with it at all yet?
We have not yet dealt with it, but that is something that we do plan to deal with it. In fact, we were debating as we were designing this API to should we have two separate bit fields, or should we have a tri-state thing where each button can go between not touched, touched, or pressed state. But I think for now, I would assume that it doesn't have that problem, and we will iterate with the hardware design and see if there's any issues why that's not true.
Great, thank you.
Hi, I was just wondering if you could say anything else about DirectX 12 and when we might see something in an SDK that we could work with. I've been using DirectX 12 myself and just a little frustrated that I can't use it with Oculus right now.
So I wish I could give you a date, but I can't, because even if I did, it would be misleading. But it is very high on our list of things to work on. The other thing I would say is that it is actually in theory possible with DX1112 interop to make this work today with 07. But we've not done anything to actually make it obvious, and we've not worked on a sample to show how it's done. This is something we will work on. But yes, this is absolutely high on our list, and we really do plan to support this pretty soon.
Okay, thank
That's
you.
all I can say. Thank you.
Hey there. I noticed the latest versions of Unity are updated to 0.7 SDK, but in Unity we access the position and such through Unity's abstracted VR classes. And on their documentation, they don't have anything about touch or the input controllers. This might be more of a question for the Unity guys, but do you know, are those touch inputs available through Unity's VR API, or would we have to, sort of redo and implement the Oculus SDK raw in Unity?
So you don't have to implement the Oculus SDK raw. We do have our own utilities in Unity that allow Unity apps to get our touch controller and button state. But we are also actively working with them to ensure that their input mechanism and their tracking objects support Oculus Touch. So this is something that we are absolutely working on.
Okay, great. Thank you.
Yeah.
Hi, Guy from Virtual Desktop. My question is, do you have plans to have APIs to define the walking area or the player height other than having the configuration utility, having a height, something like that, so that we can define zones where people can navigate in, even though it's small?
So we're not yet sure if we're going to have anything around walking area and so on, but we're definitely going to have more about user metrics like height and try and make sure that with touch controllers and our trackers, you know the exact positioning of where the headset and touch controllers are, so you can build things where the ground plane matches what the end user would expect and so on, so you can get the metrics of those things. And so there'll be a calibration step that will allow us to make sure that we know how high the user is and the headset is and so on.
Okay, perfect, thank you. And
Yeah.
just a note, the distortion primitives, having sphere Q maps, that would be very, very helpful. Thank you.
Okay, cool.
Hi there, yeah, James, Janus VR. Nice talk.
Thank you.
My question relates to the asynchronous time warp with preemption. It seems like an ideal solution for a case where you have a single frame where you've kind of gone over and missed the VSync. But say you have say 5 or 10 consecutive frames where it's missed. Are you stuck with those textures you've updated 10 frames back and you only have the updating by a rotation happening? Or it seems it would be ideal to actually render frames even though you miss and you get every other. Anyway.
Right. So ATW, as we're envisioning it, would pick the last rendered frame. So just because frame 1 made it and frame 2 didn't, by the time frame 3 is drawn, if frame 2 did complete eventually, we would pick up the most up-to-date frame. And so there are a couple of interesting, tricky aspects to this of exactly what policy we pick, because trying to decide if we want a variable frame rate or throttle it in between full rate and half rate, there's some interesting trade-offs on how that looks with timing prediction and just those transitions, how they feel in VR. So we're experimenting with that. But the goal is not that if you have 10 frames missed in a row, we'll pick 10 frame old data and just keep time warping that. That's not the plan. The plan would be to pick up something much more newer.
Thanks.
Yep.
Hi, just to touch on what was mentioned earlier about the curved surfaces versus the quads. In the design meeting yesterday, they were talking about how quads, especially larger quads, are difficult to view in VR because of the oblique angle at the edges and because they're effectively further away. Is there a plan to support things like a layer that is a parametric surface or even a mesh on which you could, like, say, render UI?
We could consider those. It's just the question of cost of rendering into those layers is to be traded off between. Like, it's easy to sample from a sphere on an arbitrary mesh. It gets more complicated as you increase the complexity of these primitives, because one of the things we've been trying to do is to ensure that our time warp distortion is really tiny, and we don't want to make this into a very big, complex, slow operation, because that's taking away from the app's render time. But yes, these are trade-offs that we're very open to thinking about.
Right, because my app, in my app, we're forced to do our own sort of layer composition of the UI in the in-world scene because we're using a curved surface, so we can't use the overlay layer.
Yeah, I would love to talk more about some of those ideas and see what we can do in future SDKs. Thank you. Great. Any other questions? All right. Thanks a lot for coming, everybody. It's great to see you, and hope to see you today.